We have all stared at a frozen screen, a loading bar that never finishes, or a program caught in an infinite loop. Software developers have long wondered if we could build a tool to detect these crashes before they even happen. This hypothetical tool is called a halting checker. You would feed it any piece of code, and the checker would analyze the logic to determine if the program will eventually terminate or if it is destined to run forever. A working checker would eliminate software bugs overnight. It would allow us to mathematically verify the safety of every line of code in an autonomous vehicle or a medical device before it ever reaches a user. This search for absolute certainty was the goal of David Hilbert's and Scheiden's problem. In the 1920s, Hilbert dreamed of finding a decision procedure, a universal algorithm that could automatically determine the truth or falsehood of any mathematical statement. Effectively, a halting checker would fulfill that dream. It would turn the act of discovery into a mechanical process, replacing human reasoning with an automated checklist that could solve any proof. In 1936, a young mathematician named Alan Turing published a proof that destroyed this ambition. He demonstrated that a universal halting checker is a mathematical impossibility. Turing's paper on computable numbers established the foundational logic of the modern computer, while simultaneously defining its limits. He proved that some processes are simply beyond the reach of any algorithm. He classified the halting problem as undecidable. This means it belongs to a family of problems for which no single algorithm can ever provide a correct answer for all possible inputs. This isn't a failure of our current technology or a lack of processing power. It is a permanent boundary in the laws of logic that will apply to every computer built for the rest of time. To understand why this limit exists, we have to use Turing's proof by contradiction. We start by assuming the impossible is true, that we have built a flawless halting checker called machine H. By definition, machine H is perfect. You give it a program, and it infallibly outputs one of two answers: halts if the program finishes, or loops if it runs forever. Now, we take machine H and wrap it inside a new, malicious piece of code. We'll call this entire combined system the crazy machine. We program the crazy machine with one rule. It must do the exact opposite of whatever machine H predicts. If H predicts a program will halt, the crazy machine is forced to loop forever. If H predicts a loop, the crazy machine must immediately stop. We have now successfully weaponized the checker's own predictive power against itself. We have created a system specifically designed to betray its own logic. The paradox triggers when we feed the crazy machine its own source code as the input. We are asking the machine to predict its own behavior. If machine H predicts that the crazy machine will halt, the outer code sees that prediction and forces the system into an infinite loop. Machine H is wrong. If machine H predicts that the crazy machine will loop, the outer code sees the prediction and forces the system to stop immediately. Machine H is wrong again. Because the machine is trapped in a paradox of self-reference, it cannot produce a correct answer. This logical deadlock proves that a universal halting checker is a physical and mathematical impossibility. While we can easily see if a simple program halts, Turing proved that no general algorithm can solve this for every possible case. This limit in computer science directly connects to the work of Kurt Gödel, who revolutionized theoretical mathematics with his incompleteness theorem. The two theories share a mechanical link. If a mathematical system were complete, meaning every true statement could be proven, you could build a program that simply lists every possible proof until it finds the one that confirms whether a piece of code halts or loops. This automated proof searcher would effectively be a universal halting checker. But since Turing proved that such a checker can never exist, it follows that mathematics must have gaps. It contains truths that no list of proofs will ever reach. We can see these theoretical boundaries reflected in the physical wires and relays of our actual machines. Computation is a rigid, organized grid of steps, but the full landscape of mathematics and logic is organic, producing structures that endlessly grow beyond the grid of any fixed set of instructions. Turing's limit protects the role of human intuition and creativity, ensuring the mystery of mathematics remains an unfolding process rather than a solved checklist.